Mabuhay, fellow physics teachers! Welcome to Physics in Everyday Life, a telecourse especially designed for us. If you recall, in one of our previous episodes, we discussed how mechanical waves are produced. We learned that a vibrating source generates waves, and we also learned that a wave consists of the motion of the particles of the medium and the disturbance which propagates in the medium. In that episode, we likewise described how these waves travel in a medium. We said that waves travel with constant velocity in a uniform medium and that the velocity differs in different media. In today's episode, we shall perform experiments to understand how waves behave when they encounter a barrier. We shall observe how their paths are changed when they undergo reflection, refraction, diffraction, and interference in this lesson on the properties of waves. Let us begin our lesson by watching ocean waves as they hit the shore. What do you notice? Do you see the waves returning to the direction from which they came? These are reflected waves. Let us watch reflected waves in a spring and in a ripple tank. But before we do that, let us first review the terms we use to describe wave motion. The crest and trough are the highest and the lowest points respectively in a transverse wave. Wavelength lambda is the distance between two corresponding points or 2 points in phase in a wave. Frequency f is the number of waves passing a point in a given time. This is also equal to the frequency of the vibrating source. The velocity of a wave describes how fast a wave travels in a medium. It is related to the wavelength and frequency, as in velocity is equal to the wavelength multiplied by the frequency, or v is equal to lambda times f. Okay, now fellow teachers, we will do our demonstrations. With us to assist in our demonstration is Leah Salvalion here. Alright, fellow physics teachers, let us observe the pulse as it hits the fixed end. What reached the fixed end? A crest or a trough? What about the returning pulse? Is it a crest or is it a trough? Did the pulse slow down or did it move faster after the reflection? Was there any change in wavelength? How about in amplitude? Now, let us compare your observation of a spring pulse with those of the water waves in a ripple tank. Watch this. Are your observations consistent? Okay, go back to the spring. We observe waves bounce back when they hit a barrier. There was a reversal of phase. That is, when a crest reaches the barrier, it bounces back as a trough. There was no change in speed nor in wavelength, but there was a change in the amplitude of the wave. Some of the kinetic energy carried by the wave was transformed to other forms. Now, consider the waves generated in a ripple tank shown here. We shall call the wave fronts moving towards the barrier the incident wave fronts, and those which bounce back the reflected wave fronts. Here is a still picture of the waves generated in a ripple tank. The line NN prime is drawn perpendicular to the barrier. This is called the normal to the surface. Now let us draw a line perpendicular to the incident wave fronts. This is the incident ray. Likewise, a line drawn perpendicular to the reflected wave fronts is the reflected ray. Note that these two rays are on the same plane. We also notice that the angle between the normal and the incident ray, called the angle of incidence, is equal to the angle between the normal and the reflected ray, called the angle of reflection, or angle of incidence I is equal to the angle of reflection R. This is the law of reflection. Now, let us use a curved barrier as shown here instead of a straight one like this. What happens to the incident waves after hitting the barrier? The pattern that you see results from the law of reflection. The reflected waves converge to a single point, the focus, in accordance with the law of reflection. What happens to waves when they pass through the boundary between two media? To find out, we will perform some experiments right after we return from this short break. Don't go away. We're back, fellow physics teachers, and we shall continue with our laboratory activities. We have here two springs connected to each other. One is soft and has a large diameter, and the other is hard and smaller. Watch a wave pulse as it crosses the boundary between the two springs. Okay, Leah? The pulse that moves toward the boundary is the incident pulse, and that which crossed the boundary is the transmitted pulse. What changes do we observe? Is there any change in the speed of the wave as it travels in the big and then in the small spring? Watch the pulse in slow motion. Is there any difference in the wavelength of the incident and transmitted pulses? Perhaps we can answer the question better if we look at two-dimensional water waves. The water in the ripple tank is divided into two regions, the deep region and the shallow region. These two regions constitute the two media. On the screen below, we can see the boundary between the two media. Compare the wave fronts in the two media. How do they differ? There are several things that we must have noted. One, there is a change in the speed of the waves as they cross the boundary between the two media. Two, there is a difference in the wavelengths of the incident and transmitted waves. Three, there is a change in the direction of propagation of the waves. We notice that waves bend when they cross the boundary. The bending of the waves as they cross the boundary between the two media is called refraction, and the transmitted waves are also called refracted waves. How do we account for refraction? As we have seen, the refracted waves in the shallow region have shorter wavelengths than those in the deep region, but their frequencies are the same since they are produced by the same vibrating source. From the equation V is equal to lambda f, the speed V is directly proportional to the wavelength. A shorter wavelength means a lower speed, and a longer wavelength means greater speed. Hence, the speed of the wave in the shallow water is less than in the deep portion. The bending or refraction can therefore be accounted for by the change in the speed of the wave as it traveled from one medium to another. Is it necessary for us to see a person so that we can hear him? Of course not. But why can we hear him even if he is not within sight? The answer when we return. Don't go away.